All right, we're back. We're still in lockdown, but at least we can talk some cosmology. So we're going to talk about one of the big mysteries of modern cosmology, which is what is dark matter? So, Geraint, are you going to scoop it for us? Are you going to tell us finally what dark matter actually is?
Well, as you know, if I knew what dark matter actually was, that's Nobel Prize territory,
Yeah.
right? But I don't. So look, I think, see that the answer is we don't know. How about we spend the discussion about what astronomers and cosmologists mean when they say dark matter? Because I've gotten into arguments about this with our friend Dr. Carl and with a friend of mine who's a philosopher of science. When an astronomer says dark matter, what do they mean? And we'll rope the particle physicists into this as well, right?
Yes, because it is slightly different.
Yes, it is. It is. And this is one of the areas which I think really gets lost in the public presentation of discussing dark matter. So let's start off with that historical context, right? So the observational evidence for dark matter, that's been building now for, it's a century, right? Because way back in the 1920s, people like Oort were talking about the fact that in the galactic disk, to account for some of the dynamics, there appeared to be more matter than stars, right? But it was really, the famous kicking off point is Zwicky's work in the 1930s. And he was looking at clusters of galaxies and looking at their relative speeds as they zip around in clusters. And he realized there must be some of this, was it dunkel material or dark matter to account for the motions of the galaxies that you see. I.e., there was more gravity in the clusters that were holding the cluster together than could be accounted for from just the stars that you see.
Right.
Come the late 1960s, early 1970s, we have Vera Rubin, Kent Ford, and here in Australia, Ken Freeman, looking at the rotation curves of spiral galaxies. And what they realized again is that the rotational speed of a galaxy like the Milky Way or Andromeda is much higher than you would expect from just the stars alone. So if you just look at like our solar system, each planet has a speed which it goes around the sun. That speed is set by the gravitational pull of the sun on the orbit of the planet. And if we try and do a similar thing with the distribution of stars that we see in the galaxy, a star like the sun is moving around the center of the galaxy at around 220, 230 kilometers per second. And if you ask how much gravity is needed to keep the sun in its orbit, to stop the sun basically exiting the galaxy, then there's just not enough gravity provided by the stars that we see. So there's this idea that there's this extra gravity which is holding stars like the sun in its orbit.
Right. So in the solar system, when we measure the mass of the sun, right, you can go and look up that number. It's a very big number, of course. The way we work that out is by watching the way the planets go around the sun, because we haven't gone and weighed everything in the sun, of course. But so there's the idea that if you know how things are moving around a certain amount of mass, you can work out how much mass there is.
That's right.
And the problem is there doesn't seem to be enough in the middle of our galaxy to hold this whole thing together. Right.
But it's not just in the middle of our galaxy, right? One of the most important observations, which gets lost when discussing this topic, the work of Vera Rubin and Kent Ford was very important, where they were looking at the motions of the stars. But in the late 1970s, an astronomer called Bosma looked at the outskirts of galaxies where he could measure hydrogen gas, and measure how fast that hydrogen gas is rotating around. And he found that it too was zipping around the center of the galaxy at around 220, 230 kilometers per second. So there has to be a lot of mass, and it's not just concentrated in the center, but it seems to be spread out over a large region, completely encompassing the galaxy that we see.
Right.
And the amount of matter is 10 times to 100 times the amount of mass that we see in the stars. So there is a lot of extra gravity in galaxies that is not counted for by just the stars that we can see.
Okay, that's an interesting point, actually. So you can't just fix the problem by putting something really heavy at the middle of the Milky Way,
No.
because then that would cause all these inner stars to go faster as well to keep their orbits. It's
Yes.
actually the way we see how the speed changes with distance tells us where this extra matter needs to be, and it's not just all stuck at the center. It's got to be spread out. Right.
Right.
What happens next?
Well, what happens next is that from the 1970s and 80s onwards is that the evidence for this additional gravity just grows and grows and grows. Not only in the rotations speeds of galaxies, but the motions of galaxies amongst themselves. So you have groups of galaxies and clusters of galaxies. So Zwicky had already noticed the clusters, but then how does this cluster and that cluster move with respect to each other? So there's this entire field of bulk flows, which is how big chunks of mass move around. But then you get observations of things like gravitational lenses. So this is where you look out into the distant universe and a foreground mass distorts our view of the background universe. And so we can ask the question, how much gravity is there that can do this distortion? And again, 10 to 100 times that's provided by starlight. And then when people measured the distribution of light that we can see from the early universe, the cosmic microwave background, and chart out the expansion of the early universe and the pattern that we can see in the cosmic microwave background, again, you need this additional gravity. So wherever we look, we find that we need more gravity than can be provided by stars and gas themselves. So we now know that there's something going on in the universe which isn't accounted for by just gravity as we understand it and the distribution of matter as we understand it.
Right. But we're talking here about, especially if we're talking about the stuff we can see in galaxies, that's obviously the stuff we can see with our telescopes, right?
Right.
So all we need is some form of matter that is just sitting there, not shining, or not showing up in silhouette to a background source.
Right. So let's be good scientists here, right? So we have observations that there's extra gravity. So we now say to ourselves, well, what are the possibilities?
Right.
And as you say, possibility number one is that there is matter out there that we don't see with our telescopes.
Yep.
So what could that matter be? Well, it actually could be normal everyday matter that was really, really cold, such that it didn't have any of the sort of transitions which produce light, right? So, a hydrogen atom, the electron has to move around to produce light.
Right.
If we've got something that's very, very cold, then maybe it doesn't emit light. Maybe it's lots of cold hydrogen clouds.
Right.
But we know that can't be right because we can measure how much hydrogen there is in the universe from basically the distribution of elements that we can see. This thing called Big Bang nucleosynthesis, the formation of the elements, is related to the amount of matter that we have in the universe. And we can't basically stuff a lot of extra matter into the universe that was there in the Big Bang and give us the distribution of elements we see today.
Right.
So we don't think it's normal matter.
Okay.
So maybe it is non-normal matter. Maybe it is matter which is not hydrogen and helium and lithium and all the other elements. Maybe it is a particle, right? Maybe it's a particle like the electron, but is somehow not accounted for in our sort of particle physics zoo because we don't have a natural sort of candidate.
Right.
Or maybe it's something like black holes. Black holes don't emit light. They have mass. So maybe they are the dark matter. Right.
Well, so let's here's two candidates. I did see this in a comment section once. Someone said, "Oh, I've worked it out. It's the neutron. Why couldn't it be the neutron?"
Well, we sort of know it can't be the neutron because neutrons have a half-life of around 15 minutes.
Yeah.
So free neutrons that aren't joined together inside nuclei of atoms basically all evaporate away in the universe in half an hour, they're effectively all gone.
Yeah.
So you need something that's going to have a half-life at least as long as the age of the universe, if not much longer.
Right.
So the
All
neutron
right.
doesn't fit the bill.
Take two. What about the neutrino?
Well, the neutrino was postulated as a dark matter candidate for a long, long time. But the problem is by the end of the 1990s, we had measured the mass of the neutrino, right? Or at least the mass scale. And we know that even though neutrinos are exceedingly numerous in the universe, they carry just too little mass to be dark matter. So the neutrino, as we understand it, as part of the particle physics zoo, they're just not massive enough.
Okay. All right. So what are the live options then?
Well, this is where we get into particle physics territory. I should also mention that black holes appear to have been eliminated as a candidate as well. There are some windows where people think that maybe these things called primordial black holes make up dark matter, but I don't think they're an overly favored candidate. So people have an idea that maybe the particle physics zoo, which comes out of our standard model of particle physics, we know it's not complete. So maybe if we push the mathematics of the standard model, we'll open up an area where we'll have dark matter candidates. And the big problem that we have, of course, is what we're saying is something like, right, imagine that we've got an equation which is x plus y equals 2, right? And where x is sort of the particles we know, and y is the particles we don't know, but we just know that it has to equal to the total amount of mass in the universe or something, right? The problem is that y, what form does y take? And in mathematics, right, there are a whole different ways that y could be, and each of those opens up a completely new window on possible dark matter candidates. So the problem that we have at the moment is that there's an embarrassment of riches. There are literally hundreds, if not thousands, of dark matter candidates that people have proposed that all have the property that they're invisible to our telescopes, and all have the property that they don't interact very strongly with all of the quarks and electrons and stuff, but don't give us real observations that we can differentiate one dark matter candidate from another dark matter candidate.
Right. And so in when you specify the physics of this thing, all you need to satisfy the data we have at the moment, all you need is it's got to be heavy, so it has that gravitational pull, and so it's not moving too fast, and it's just got to not emit too much light or interact with things that are emitting light too much.
That's right. That's
and
right.
There's a lot of space there to just make up your own novel.
Exactly. So now we run up against a boundary, okay? So in many physics departments, you will have astronomers and you will have particle physicists. And if you put the ear to the door, you might hear some astronomers talking about dark matter. And if you put the ear to the door, you might hear particle physicists talk about dark matter. And one of the startling things to realize is often they're not really talking about the same thing. In the sense that they are talking about the fact that there is dominant mass out there in the universe. And to an astronomer, dark matter is this dominant mass which does, pulls on galaxies, etc. And in their mind, they have a particular picture. They call it the cold dark matter paradigm, right? So what they mean is that there's this dark matter stuff made of particles, and it's cold, meaning that it doesn't zip around, okay? So that means it has the right kind of clustering properties. And to an astronomer, they're happy and off they go, right? That's what dark matter is. But then when you talk to the particle physicists, they love all of these different possibilities, right? So for them, dark matter may not be just a single dark matter particle, but dark matter might signify an entire species of particles that have these properties of being not visible to our telescope and weakly interacting. But within their own little dark side of the universe, there could be all of this other dark physics going on. And so these dark particles could have dark atoms and dark light and all these other interactions. So they're after this potentially rich, hidden physics in the universe. So, they're proposing that there could be all of this hidden physics, and they're wondering about how this physics could be revealed through observations and experimentation.
Right. I asked this of a particle physicist once, but in order to explain our observations, we still need that dark matter to be all sort of spread out through our galaxy in a way that's more spread out than the stuff we're made out of is. We know at least that much. So there can't be two... The reason why our stuff is more condensed and collapsed in galaxies is... Well, why it is condensed and collapsed is in part because it interacts with itself, and so it can send out... It can give off energy and collapse and radiate some more energy and keep collapsing. So presumably the dark matter sector can't do too much, or it might start collapsing as well, and then it doesn't do the role it's supposed to do. Do we have handles on that sector?
Well, some people have proposed that there is self-interaction of dark matter and self-annihilation, and that there is structure in dark matter. Now, already astronomers acknowledge that if it's their cold dark matter picture, you do get clustering and lumps of dark matter in a whole range of scales. Yeah. So if you can already imagine you've got this fractalish kind of structure, then what goes on at the small scale? And, there have been more almost science fiction suggestions that, of course, you get dark life, that you would get interactions on a scale that could produce complexity and life. But again, particle physicists talk about dark matter one way, astronomers talk about dark matter another way, and they are not always talking about the same thing.
Right. And on top of that, there are some astronomers who are not talking about dark matter at all.
Oh, and again, this is a minefield, of course. We already said we have got to talk about the possibilities. And one possibility is that dark matter is matter. But of course, what we're talking about is explaining missing gravity.
Right.
And another way to explain missing gravity is to say that the mathematical equations you use to describe gravity are incorrect or aren't complete. And so there's this entire side of astronomers, theoretical physicists talk about basically modifying gravity. So to them, there is no physical substance out there, which is matter, that accounts for the observations. What is missing is our correct description of gravity.
Right.
So now, again, that's often seen as being much more of a fringe topic.
Yeah.
Because, again, you run into this problem is how do you tell the material dark matter from this missing gravity dark matter? And at the moment, the observations are all a bit wishy-washy and really either goes. And, astronomers and physicists sort of play this Occam's razor game and are happier to think that there is a dark matter component to the universe, which is material, than that we have to give up our picture of gravity as we understand it.
Yeah.
But of course, we know that our picture of gravity can't be complete. And so, in reality, when an astronomer says dark matter, what they're saying is that I have a component of the universe that I'm ignorant about.
Right.
I'm putting down a bigger bet that it's a material thing. But honestly, I'm keeping a little bit on the side because it could be that we just don't understand gravity correctly.
Yeah.
So, very few astronomers, I think, would say dark matter is definitely, I bet my house on it, a cold, massive particle. I think we know one or two that would, but I think most would say, oh, I think it's a particle, but I'm not 100% sure.
There is precedent for this in the solar system, actually. So around the middle of the 1800s, observations of Uranus showed that it wasn't quite where we thought it should be if we're solving the equations right of Newtonian mechanics, as it was then, Newton's ideas about how to do gravity. And So people looked at the options, and again, it was this: there's something about gravity that we're missing, and so one of the options is Newton was wrong, and one of the other options was maybe there's something else out there which is pulling on Uranus, which we didn't know about. And so they actually did the calculations. Well, if it's pulled on it in just this way, it must be over there. And then lo and behold, that's how we discovered Neptune to within about a degree, which is a remarkably, it's an amazing bit of astronomy. But then it happened again towards the end of the 1800s, early 1900s. Mercury, this time not way out wide in the universe, but in close to the sun, it wasn't quite where it was supposed to be. And so we went through the whole thing again. Maybe there's a planet in there that we haven't seen before, which is pulling on Mercury, and it didn't turn up. Actually, a couple of times it did, and then it didn't turn up again. Some people say they thought they saw it, and then other people checked, and then what happened at the end there was Einstein came along and said, "Here's my new picture of gravity." But the reason it explained why Mercury is doing what it's doing. One of the reasons why Einstein's answer was embraced by almost everyone so quickly is it's such a beautiful and simple theory, and these modified gravity theories strike most, I think most astronomers and particle physicists as being quite ugly. It's not a nice, natural, neat solution.
But if somebody could come up with a nice, neat, natural solution, a mathematical solution, I think, astronomers would be over it like a rash, right? And physicists as well, right? If we had a new theory of gravity that did away with dark matter and dark energy, we'd all sort of go, oh, okay, so that's really what's going on.
Thank goodness.
Yeah. And, some people would be a bit upset. But I think most people would sort of go, yeah, I always had a small bet that would be the case.
The other option is, in one of these particle physics models, maybe we see some evidence. Maybe it interacts with our type of matter very rarely, but maybe it's just enough that we just see a signal. So there's loads of experiments trying to do that as well. So that could be a way where dark matter actually wins the day.
Yeah. Oh, well, I said I haven't actually put any money on the table with regards to this. I would potentially bet a car that dark matter is material, but ain't going to bet the house.